be difficult to understand option Greeks intuitively without understanding the language in which they're written, which is mathematics. But there is no need to go back to school or pick up a textbook. All that is needed is a conceptual understanding of a few tools from calculus that reveal the essence of option Greeks. Now let's begin with our brief journey into calculus. We'll start with a simple function, say f of x equals 2x plus 1. The question we want to answer is, what is the slope of this function? Well, isn't that the same thing as asking for an increase in x? How much does f of x increase? We can answer this by measuring the change in x, which we can call dx, short for delta x, with delta meaning change in mathematics. And we can compare that against a corresponding change in f of x, called df for delta f. The slope would then be how much our function increases for each unit it moves forward. In other words, it would be df over dx. In this case, that would be 2 over 1, or just 2. What we just did here, finding the slope of this function, is called differentiation, or taking the derivative of the function. We could think of differentiating a function as an operator applied to the function, the notation for which is often expressed as the ratio d over dx. For this function, we would apply it to both sides to get d over dx of f of x equals d over dx of 2x plus 1. The left side becomes df over dx as f of x is the dependent variable, while the right side becomes the derivative with respect to the independent variable x, which is just 2. The 1 disappears because the change with respect to x of a constant is, well, a constant doesn't change ever, so it is 0. We can see that if we plot the function f of x equals 3. As you can see, a flat line with no slope. The derivative of a constant is going to come up a lot, so it is a good idea to keep this in mind, or you might find yourself asking, why did that go away? Since we can apply this differentiation operator to almost any function there is, let's try it with something more complicated. Here we have the function f of x equals 1/10 x to the fourth minus 2x squared plus 1. What is the slope of this function? Well, the answer is not so easy here, as the slope is not a constant value, but rather keeps changing. However, let's not be discouraged just yet. We can draw a tangent line at x equals 0, and measure the slope of that tangent line, and plot the slope of the tangent line on a separate set of axes. If we sample enough points, and keep plotting the slopes of those points on the separate axes, then perhaps a pattern will emerge. And one does. Sampling some points shows us that the slope is the function df over dx equals 4/10 x cubed minus 4x. Well, not really. I clearly knew the answer, as it would be rather tedious to figure this out from a sample of points. So is there a more efficient way to calculate derivatives directly without the need to sample points? And there is. There are a set of rules for taking the derivative of a function, the most notable of which are the power rule, the product rule, the quotient rule, and the chain rule. We are not going to go into detail on how these rules work, as the purpose here is conceptual understanding, not calculation. The important thing to know is that using these rules, we can take the derivative of almost any function. But does that mean that we can take the derivative of a derivative? I mean, if the derivative of a function is another function, and using these rules, we could take the derivative of almost any function, then it would make sense that we could take the derivative of a derivative. And we can. Applying these derivative rules to the derivative, we would find that the derivative of the derivative is the function d squared f over dx squared equals 12/10 x squared minus 4. The notation d squared f over dx squared is a notation for a second derivative. Likewise, if we repeated the process to get the third derivative, we would get d cubed f over dx cubed equals 24/10 x, with d cubed f over dx cubed being the notation for the third derivative. One pattern you might be noticing is the power rule. The power rule is quite simple and just says that if you are taking the derivative with respect to some variable, let's say x, and that variable is raised to the power of some number, then the number just hops down in front and the new power is decremented by 1. So the derivative of f of x equals x cubed becomes df over dx equals 3x squared. And if we take the derivative again, then the 2 hops down and is multiplied by the 3 that is already there to give us d squared f over dx squared equals 6x. To take the derivative again, we have to realize that x without a power actually means x raised to the power of 1. And so the 1 hops down and is multiplied by the 6. The x then goes away because we decrement the power to get x to the 0, and anything raised to the power of 0 is just 1. But back to the second and third derivatives. Just what is a second or third derivative? How do they relate to the original function? And can they tell us anything special about that function? We know that the first derivative is the rate of change of the function. So the second derivative is the rate of change of the rate of change of the function. But that doesn't really tell us much. Let's see if we can find some relation from examining their plots. It does appear as though the second derivative is positive when the function is convex, meaning that the inside of the curve is facing up. And it appears as though the second derivative is negative when the function is concave, meaning that the inside of the curve is facing down. And in fact, the second derivative of a function is generally interpreted as the curvature or convexity of the function. While mathematicians use the terms convex and concave to describe the curvature of a function, in finance, curvature is typically referred to as either positive convexity or negative convexity, and the word concave isn't typically used. Since convexity is an important concept in finance, including option Greeks, let's take a minute to wrap our heads around exactly what convexity is and what it tells us about a function. Let's take the function f of x equals 1/2 times x squared. As we change the coefficient in front of the x term, then we get differently shaped parabolas. When the coefficient is small and positive, for example 1/2, then we get a small positive convexity, which indicates that the curvature of the function is upward facing to a low degree. If we increase the coefficient, then the convexity increases quickly, indicating a function with a high degree of curvature. If we flip the coefficient to negative, then we get a negative convexity, with numbers close to 0 giving us a small amount of curvature, and therefore a convexity number also close to 0, and with a number far from 0 giving us significantly negative convexity. And if the coefficient is 0, then we have a straight line which has a convexity of 0. While it is easy to analyze the convexity of a parabola, when we switch to option Greeks, we will need to analyze the convexity of more complicated functions. But if you keep in mind the simple example of a parabola, then making sense of the convexity of a more complicated function will be easier. Going back to the polynomial function we were looking at before, the third derivative is often interpreted as the smoothness of the function. And we see that here with the function initially dropping rapidly, but at a slower and slower pace, resulting in the third derivative being very negative. Then the function stabilizes and the third derivative is close to 0. But then the function gains momentum and even increases dramatically and the third derivative rises. While the third derivative can be thought of as the smoothness of the function, it is typically used to analyze the features of the first and second derivatives, which is how we will typically see them used with option Greeks. One last question to answer in single variable calculus is, what is the derivative of the sum of two functions? Well, if the two functions are both lines, then it is easy to see that the derivative of their sums is the sums of their derivatives. That is, if the two functions are f of x equals 2x and g of x equals 3x, then the sum of those functions is 2x plus 3x, which equals 5x. Likewise, the derivative of the sum is 2 plus 3, which equals 5. So the derivative of the sum of two lines is the sum of their derivatives. But is this also true for more complicated functions? Yes, it is, and it is known as the sum rule. This will be important when we tie everything back to option Greeks, so make note of the sum rule. Last thing to mention is that the color scheme has a meaning, and here it is. So for example, all first derivatives will use the same blue, green, and yellow gradient. That way it is easy to identify when you're looking at a first derivative. And this will carry over once we tie everything back to option Greeks. The reason I use gradients rather than solid colors is just to make it easier to see detail. Solid colors can sometimes make it difficult to pick out details in the plots, especially once we move to three-dimensional plots in the next video. Now that we have a decent grasp on what a derivative is for a single variable function, we'll extend this to multivariable functions in the next lesson. I would like to give a special thanks to those who support this channel on Patreon, especially for the comments they provided on early versions of this video.